start getting awards just because you have other awards. And that means retirement is on the horizon. Just, yeah. But thank you, Jack. Thanks for the introduction. Thanks for the invitation to come here. As I've been explaining to folks during the day, over the last 30 years, I've had numerous opportunities to visit Ohio State and always enjoy the interaction. So again, I appreciate the welcome. I'm here to talk to you today about the field of hypersonic flight, and I want to start out with a little bit of audience participation. I just want to see a show of hands. How many of you know what hypersonics is? Wow, okay, great. That's going to make the rest of this talk much easier. But for those of you who don't worry, I'll tell you a little bit about what hypersonics is, why it's important. I'm going to do a little bit of mix of technology. I'll tell you some of our technical challenges, but also talk to you about some of the policy issues, and frankly, not only the national perspectives, but the international perspectives that make this such an important issue. As Jack mentioned, up until about a little over a year ago, I was in the Pentagon. I had a job that was called the Director of Defense Research and Engineering to oversee modernization of the department. That was a job where basically my role was to make sure we got the right modernization technologies into the hands of our warfighters. And that's everything from artificial intelligence, to advanced microelectronics, cyber, autonomy, directed energy, you name it. But hypersonics is really at the very top of our list of priorities. And it was there because of the impact that it can have on the future of military engagement. So that will be the bulk of my discussion today. All right, so let me start out with, let's make sure we're all on the same page. And first ask the question, what do we mean by hypersonic? Turns out there is no fixed definition of hypersonic. There's a fixed definition of subsonic, that means flow slower than the speed of sound. There's a fixed definition of supersonic, which means flow faster than the speed of sound. Hypersonic is generally high supersonic. So we usually say it's flight many times the speed of sound. What does that really mean? Maybe about 5 times the speed of sound. Some people would argue 4, some would argue 6. It doesn't matter, it's splitting hairs. But think in terms of 5 times the speed of sound. Put another way, for an air vehicle, it means flying at about 1 mile per second. So that's the mindset. If you're doing Mach 5, you're traveling at a mile per second. And there's a number of attributes that are associated with flying in that regime. And again, I'm sure many of you in this audience are familiar with that. Whenever you fly faster than sound, you generate a shock wave in front of the vehicle. As you fly faster, that shock wave gets pressed closer and closer to the vehicle. At hypersonic speeds, those shock waves are pressed very close to the vehicle. Heating becomes really important. When you fly at these speeds, skin friction with the air leads to heating, especially on sharp leading edges in front of the vehicle. And so that has to be taken into account. That drives you to using high temperature materials. At some conditions, the temperatures become so high that chemistry of the air becomes important. So you have to, when calculating the flow field on a hypersonic vehicle, you have to take that into account. Now, in modern parlance, when we say hypersonics, it's generally shorthand for a somewhat more complicated description, which is a hypersonic vehicle that also operates at long duration in the atmosphere. And I'll explain what I mean by that in a little bit more detail, but there are hypersonic vehicles. Someone wants to send me an email, so let's not do that. All right, there are examples of hypersonic vehicles that spend very little time in our atmosphere. For example, any spacecraft that's coming back from orbit is entering the atmosphere at hypersonic speeds, but slowing down very quickly and spending only a few minutes under those conditions. In modern parlance, we were referring to a class of vehicles that are spending a lot of time traveling at those speeds, which means they have to handle the heat loads, they have to have a propulsion system that's going to continue to propel them through the atmosphere, and all the associated engineering challenges. Today, there are basically 2 approaches that we can take to flying at hypersonic speed. On the far side, you see what's called air-breathing propulsion. That is having a jet engine that somehow powers you as you barrel through the atmosphere at Mach 5 or above. The engine of choice that we think is the secret to powering hypersonic vehicles is something called a scramjet, a supersonic combustion ramjet. By the way, it's the best name for an engine ever conceived of. I mean, what's better than a scramjet? It's a very simple engine. It's got a hole in the front. Air comes into that hole. Fuel is injected. It mixes. It burns. The hot gases expand out the back. The other approach is to take is relatively simple, which is I put my hypersonic vehicle on top of a rocket. And I use the rocket to accelerate up to speed, and then I separate the vehicle off the rocket, and I glide to wherever I'm going. If it's a weapon, I glide to a target. If it has some other use, I glide to wherever I want to use that system. And both of these technologies have pros and cons, have advantages and disadvantages. And both of them are the focus of current work in the field. All right, so I want to, before we get into those two approaches, I want to actually ask the question, why would you want a jet engine? Why would you want a scramjet, an engine that operates using an inlet with air coming in the front? And this is a chart that very famously was first derived by a gentleman named Tom Curran, who worked at the Air Force Research Laboratory. We sometimes call it the Curran plot. And this shows a measure of engine performance compared to the flight model. And that measure of engine performance is something called specific impulse. Defined very simply as the amount of thrust that you get divided by the rate at which you consume fuel. So it's bang for the buck. It's how much thrust I get from the amount of fuel that I burn. And to note, rockets have specific impulses. The units work out to units of seconds. Rockets have specific impulses that top out at about 460 seconds. So that's, and that's the most efficient engines that we can build today. Jet engines do much better. Jet engines can operate in the thousands of seconds of specific impulse. For the very simple reason that we're not bookkeeping the oxygen as part of the fuel mass. Right? On a rocket, everything that's burning in the combustion chamber is carried inside a tank. For a jet engine, only the fuel is in a tank. Everything else that burns with it, the oxygen in the air, is being swallowed from outside. So that gives us a higher specific impulse. And you see, as you move up the Mach scale, there's this tendency for specific impulse to drop, but it always remains higher than a rocket. And even that scramjet engine that I described can be a factor of 2 or 3 better than a rocket. That means I get 2 or 3 times the thrust for the amount of fuel that I'm burning compared to a rocket system. So that, in a nutshell, is the advantage. Right? I can go further on a tank of gas. All right, so given this range of applications, let's talk about what you can actually do with a hypersonic vehicle. Why would I want to build one of these things? And I'll put them into several different categories. First, any planetary entry system. That's our Apollo spacecraft, space shuttle, any of the probes that we send to Mars, the outer planets. When they're entering the atmospheres of those planets, they are hypersonic systems. But those are hypersonic systems that are designed to slow down. Right? When a spacecraft is coming back from orbit, you want it to slow down so it decelerates, eventually lands on the planet. That's very different than the other systems that I've shown in this slide. In those categories, put three bins. First, weapons, things like cruise missiles, high-performance missiles, aircraft, they can be manned or unmanned, and then ultimately spacecraft. Things that can launch payloads all the way up to orbit with an airplane-like operation. I'm not going to say much about this category because this is almost on the verge of science fiction. This is the far-reaching category. When I was a student, when I was a graduate student, the United States had a program to build a vehicle that would do this, basically take off like an airplane and fly up into space, deliver a payload, and come back and land. I'll show you some details of that program. But we realized, as that program was progressing, that this really was a bridge too far. There were too many miracles that had to happen in order for this type of vehicle to work. Aircraft are somewhat closer, right? A space vehicle has to fly up to 25 times the speed of sound, be in orbit. An airplane, you can imagine a hypersonic airplane that flies at maybe 5 times the speed of sound. Still accomplishes an interesting mission. It could be a sensor mission, it could be a reconnaissance mission. It could deliver payloads or people to remote parts of the planet. The reality, though, is the area that most people are focused in right now is really on the far side of the pie, it's the weapons, because that's the low-hanging fruit. It's also the one that's captured a lot of attention from around the world. So that's the one where most of our efforts are focused right now. So I mentioned that when I first started, when I went back to the Pentagon, I had a list of modernization priorities. I just want to put this in context so you understand why hypersonics is viewed as being important. Every 4 years, the Secretary of Defense releases a document that's called the National Defense Strategy. And in most cases, honestly, these are pretty meaningless documents. They're kind of motherhood and apple pie. Defense is important. National defense is, critical. In 2018, though, something interesting happened. The National Defense Strategy that was released did a deep dive in a number of key areas. One, it looked at the competition around the world. It did an assessment that said, up until this time, the Department of Defense was focused on the war on terror. It was focused on counterinsurgency. And this document said, well, that's important, but much more important is pure competition. And there were 2 countries that got singled out, Russia and China. And as we've been watching the events in in the world today, you can see that that was somewhat prophetic. So that was, wow, your campus system really wants to connect to my computer. That is persistent. Okay, but another thing that came out of this document was a list of technology areas that were critical to the future of national defense. And some of those I already mentioned: microelectronics, AI, autonomy, cyber, network command and control, communication, quantum science was on that list, biotechnology was on the list. I'll tell you very quickly, when I got to the Pentagon and I started talking to people about biotechnology originally, the response I typically got, especially from the services, was, well, yeah, that's really interesting. But, you know, we're the Air Force, we don't do biotechnology. We're the Navy, we don't care about biotechnology. And then COVID-19 hit, and everyone got really interested in biotechnology. But you notice I highlighted hypersonics, and that was also on that list. And this document made this a definitive statement that essentially said, if we do not pursue hypersonics, the U.S. military would be at a disadvantage. Now, that document is 2018. It was begun in the Obama administration. It was released by Secretary Mattis in the Trump administration. So it actually crossed over 2 administrations. And most recently, the Undersecretary of Defense for Research and Engineering, Heidi Shyu, released her new list of technology priorities. And hypersonics is still at the very top of her list. So this is something that has transcended multiple administrations. And I'm just going to tell you as an aside, that's really quite remarkable. There is this tendency in Washington, when a new administration comes in, they will look at what the previous administration did, and they'll say, okay, we're going in a different direction. And that didn't happen this time. This administration came in, looked at that list, and said, yeah, it's about right. In fact, I'll tell you a quick anecdote, which is when Heidi Shyu came in as the Undersecretary, you know, we were kind of passing the torch in the transition process. She said, you know, there are all these priorities that seems like too long of a list. We kind of need to narrow it down. And when she released her list, she actually added to the priority list. So she realized that, you know, there are a lot of things the department has to do. But the important point is hypersonics continues to be important. Okay, so now let's step back and talk a little bit about the history of the field. Where are we? How did we get here? Hypersonics is not a new area. We have been flying hypersonic vehicles since the late 1940s. So that's a picture of a fellow named Frank Molina, who was the project lead on something called Project Bumper. Now, what they basically did was, right after World War II, they put a sounding rocket on top of a captured German rocket, the V-2 rocket. And they eventually flew that thing up to Mach 6 times the speed of sound. And then Frank Molina ultimately decided he wasn't interested in being an aerospace engineer anymore, and he moved to France and became an artist. But before that happened, apparently a funny story, but before that happened, he accomplished what we believe is the first human-built flight of a human-built hypersonic vehicle. Throughout the 1960s, NASA, the Air Force, and the U.S. Navy flew a vehicle called the X-15 rocket plane. If you drive to Dayton, Ohio, and go to the Air Force Museum, and by the way, if you're in this room, I hope you have at some point in your life gone to the Air Force Museum. If you haven't, I'm going to give you that assignment. You need to go to the Air Force Museum. If you go to the Air Force Museum, you'll see that very vehicle on display. It was an amazing program. 3 X-15 vehicles were built. They were flown over a period of about 10 years, 199 flights. It still holds the record for the highest human-occupied, the fastest human-occupied vehicle in the atmosphere at almost Mach 7, almost 7 times the speed of sound. Of course, as I mentioned earlier, everything that comes back from space is entering the atmosphere as a hypersonic vehicle. The fastest Earth entry that we've ever done was Mach 43, 43 times the speed of sound. That was a probe called Stardust. There's a very frustrating story about Stardust because before this mission, NASA wasn't fully instrumenting all of its re-entry systems. And there were a number of us who really pushed on NASA to start doing full instrumentation because we said, you know, if you're coming in at this level of energy, there's a lot that you can learn. And unfortunately, they didn't instrument Stardust before it flew. So after it came back, there was a lot of study done on the heat shield. But because we hadn't done the study before it flew, we didn't actually have we had the after, but we didn't have the before. That was a little bit frustrating. But still, nowadays, there's a new rule at NASA, which is every time you fly one of these missions, you instrument it so that you can get aerothermodynamic data. The scientists don't always like that because if you're putting instruments in the heat shield, that means you're putting holes in the heat shield, or so the folks who are worried about the data coming off the satellite push back hard. But I mentioned Apollo, so the Apollo 10 was the fastest manned entry, 37 times the speed of sound. And then more recently, I'll talk in more detail, in the mid-2010s, the U.S. Air Force flew this vehicle, you see in white, which was a vehicle called the X-51. That flew at 5 times the speed of sound, did so for a total of about 143 seconds the first time, and then a fourth flight in 210 seconds. It was really quite a breakthrough in the field. So, main message here is hypersonics is not new. I mentioned the X-15 program. I still highlight that as the gold standard for experimental flight vehicles. As I told you, 199 flights. Its pilots included Neil Armstrong. A couple of years ago, there was a movie that came out, a biography of Neil Armstrong. They actually start the movie with Neil Armstrong flying the X-15. And that was his entree into the astronaut program. A lot of interesting lessons learned from this program, not the least of which is they weren't risk averse. For those of you who find yourselves at some point in your career doing flight testing, the folks around this program didn't take stupid risks, but they were willing to take risks. They were willing to push the envelope. When bad things happened, they figured out why, they fixed them, and they flew again. At one point in the program, one of the X-15s touched down and landed a little bit hard, and actually broke in half. And the response was great. We wanted to build one a little bit longer anyway. So they actually rebuilt the vehicle with a center section where it was broken in half. And that's an example of the engineering that they applied. All right, so what is different now? What is driving all this push? Why does hypersonics keep appearing on the list of key technologies? Well, there are several factors. One of them is we've got competitors. Russia and especially China have been investing very, very heavily in hypersonics. These countries have different takes on the field. So Russia had a long history of working in hypersonic aerodynamics, going back to the 1950s. As we were developing the field and developing methodologies in order to build intercontinental ballistic missiles, so were the Russians. And some of the classic papers in the field were written by Russian researchers. One of the classic textbooks, for example, was written by a researcher named Cherny, who started working in the 1950s. And the Russians have continued to work in this field, although they've had a renewed enthusiasm in recent years. Vladimir Putin himself has bragged about Russia's hypersonic capabilities. He just recently, just last week, cited hypersonic systems as weapons that he was threatening to use in the invasion of Ukraine. China's a very different story. China got to the field relatively recently, and they've just done huge investments. They built on a lot of the work that they saw around the world. They invested in people, they invested in facilities, they invested in their universities. And in 2019, they proudly showed off some of their hypersonic systems. This is you see a picture from a parade, the military parade that the Chinese did in Beijing. And right there is a weapon called the DF-17, which is a fully deployed hypersonic system. We in the United States don't have fully deployed systems yet, but China does because of this investment that they made. So as you can imagine, something like that gets a lot of attention. Frankly, meanwhile, over here in the United States, we haven't been doing so well. I'm going to walk you through a list of failures. So in the 2010 era, DARPA had a program to build something called the HTV-2, Hypersonic Test Vehicle number 2. They flew it twice, it failed twice. More recently, there is this report from about a little over roughly 2 years ago of a DARPA program where they're doing a test flight, and the reporter claimed that the test article actually fell off the airplane before it ever flew. It turns out it didn't fall off the airplane, but the real story is almost worse. So that's not good. You see other failures. However, we've also had some successes. And in September, Northrop and Raytheon flew a hypersonic system called HAWK, and it was a very successful flight. So the message here is the United States took a pause, but it's getting back in the game. And we can ask the question from a policy standpoint. So what's going on? Why do we have countries like Russia and China that are moving so quickly, and yet we're not? And I'll offer a couple of insights. One is funding in the field has not been consistent. It has followed this periodic cycle, and I'll show you a chart of that in a moment. Sometimes we've been a little bit over-enthusiastic as we pitch programs, where we've had this habit, the community's had this habit of promoting ideas that are maybe require one or two extra more miracles than we can possibly pull off. And then finally, this one is really frustrating. even when we've had successful programs, we haven't always capitalized on those successes. I mentioned the funding cycle. So a friend of mine, Dick Hallion, who was the Air Force historian for a number of years, actually plotted out funding in the hypersonics field. And you see it's got this periodic cycle. It's about a 15-year cycle that corresponds to major programs. And you see, program begins, we put a lot of money into it, we end the program, we stop funding it. And then new programs start, more money, and then we stop funding it. And as you can imagine, this impacts not only the investments that the government have made, but the investments that industry will make. It also impacts workforce. Right? If you're a student and you're here seeing the downward trend, you might think, well, hypersonics is maybe not the most lucrative field. Now, you will note, 2020, notice how well we're doing. And that's because of the concern that was raised about peer competitors. The astute among you should ask the obvious question, okay, so that's going up. Does it keep going up? Does it level off? Or does it do another turn? In fact, all of your faculty members who work in hypersonics are asking that question. Is the funding going to continue? I'm going to argue I think the funding will continue because of the fact that we've got competition. So I think it's pretty stable. All right, so let's step back and talk about some other mistakes that we've made. I mentioned the National Aerospace Plane Program. I want to take you back. I was a graduate student in the 1980s, and President Ronald Reagan goes on national television and announces that the United States is going to build a vehicle that will take off from any runway and fly up to orbit with a single stage. And it was going to do that with scramjet engines. And it came out of a DARPA program. The vehicle, as originally conceived, is shown here. This was the baseline design. It's going to be about a 50,000-pound vehicle. And remember, this thing had to fly up to orbital speed, which is roughly 25 times the speed of sound. All right. When the program was canceled in 1993, it had grown to 450,000 pounds from 50,000 pounds. Those of you who've taken an aerospace design class, a good rule of thumb, weight equals cost. So the bigger your vehicle, the more expensive it's going to be. So this was a huge increase in expense. And by the way, the deep dark secret of this vehicle, it really couldn't make it up to orbit. They could never figure out how to get it up to the speed required to get to orbit. The design didn't close, and so that was the end of the program. An example of biting off more than we could chew. And again, I don't want to keep belaboring this, but we've had other examples of programs that were kind of biting off more than they could chew. DARPA programs, Navy programs. Some successes, but even the program that I'd like to highlight as successes had a couple of failures before we actually got to the final flight, which was a successful flight. At the same time, we've had some notable advances in the field that I'm going to point out to you. In 2002, a university team working in Australia, in the outback of Australia, based out of the University of Queensland, flew the first supersonic combustion ramjet. Now, there were folks who criticized the flight saying they produced thrust, but thrust wasn't greater than drag, fine. But they still showed that this idea of a jet engine that could power you at high Mach numbers was viable, didn't violate the laws of physics. And I kind of think of that as a milestone. I also love that example because this was a university team that was funded to the level of about $1 million. And they flew a scramjet before any of the really expensive national programs. So it shows you what a dedicated university team can accomplish on a shoestring budget. Other successes, NASA flew this vehicle called the X-43. That was 2 years after the Australians. That was a full flight vehicle. And there they had thrust greater than drag. So this is often referred to as the first time we flew an air-breathing hypersonic vehicle. And then other successes, this is in the rocket boost flight area. This is something called the Advanced Hypersonic Weapon, which flew first in 2011. We've had multiple flights since then, 2017, 2020, some more recent flights. That's not powered by a scramjet, but it's still a very high lift, very low drag, slender configuration, flying a very long distance at hypersonic speeds under extraordinary thermal conditions. Once again, proving out the technology. I want to hammer home the importance of X-51, which was the Air Force program I mentioned. X-51 had 4 flights. It built on the expertise of the X-43 that NASA did. It was different, though, in that whereas the NASA vehicle only operated for a handful of seconds, it's only about 11 seconds for each of its flights, X-51 flew finally for almost 210 seconds under scramjet power. That was important because it showed that you could fly at hypersonic speeds in the atmosphere for a long period of time. And remember the rule of thumb, you're flying at Mach 5, you fly a mile a second. So they covered almost over 200 miles in the period of time when the engine was operating. Really quite a remarkable accomplishment. So, all right, let's step back once again. We have flown hypersonic vehicles. We've shown hypersonic vehicles can be built, they can operate, other countries are deploying them. Let's talk about how the field has now changed from a fundamental science standpoint. And I picked the point in time, 1988, because that's when I was finishing up as a PhD student. So you can all do the mental math and figure out that I'm old. We had a list of questions about this whole field that were really big unknowns. First being, could a scramjet engine even work? Did we even know if it could operate? Could an engine survive if it was designed with a weak oblique shock wave and then spit out a strong normal shock wave so you hold it unstart? We didn't know how to squirt fuel into the engine. We didn't know if leading edges would get so hot that they would melt. We had no idea where the flow on the surface of the vehicle would go from smooth and laminar to turbulent. All these issues, we didn't know if the vehicles would be controllable. We didn't even know how to do a fully integrated design. We didn't even know what the front end of the engine should look like. Here we are in 2022, and I'm happy to say that over the course of decades, we have learned a lot in the field. We have made this an operational technology. We know scramjets work. We've flown them. We flew an X-43. We flew an X-51. Other people have flown scramjets as well. We can survive on starts. We can inject fuel. We can get it to mix and burn. We can build leading edges that handle high heats. We're still trying to solve problems related to boundary layer transition, figuring when the flow is smooth and laminar, when it's swirly and turbulent. But we've made a lot of progress in that area. And on and on and on. So we really, I would argue, we have a very proud record over the past few decades of working through this. And this is a whole of nation effort. A lot of it centered at our universities, including work right here at The Ohio State University. A lot of this work was done at places like Purdue University, University of Michigan, Texas A&M. Really, it's been a concerted effort, which is a tribute to our community. All right, and given that, there have been some policy documents that were then derived that said, okay, we believe this technology is deliverable, can be made operational. Therefore, what are the implications? A key milestone. In July of 2014, the United States Air Force released this document. It's called A Call to the Future. And it was projecting what the future of military operations would look like. And it included a list of technologies. And the number one technology that they list was hypersonics, and that's the picture of X-51. So that was the good news. The bad news is lots of other people were paying attention. They read that document. I've often pointed out that corresponds with the start of work at big effort levels in China and in other countries. And very soon after, China started being very, very open about the work they were doing in hypersonics, bragging about some of the tests they were doing. Russia, even in 2016, Putin was talking about their hypersonic work as well. So, in many ways, we did the worst of all possible things. We, the United States, told the whole world, hey, this is key technology. This is the future of the military. And then we let people read those documents, and they said, yeah, hey, this makes sense. And they started investing, at a more enthusiastic rate than we are. I'll show you another indication of this. All right, so how many students in the audience are members of the American Institute of Aeronautics and Astrophysics? All right, good show of hands. So AIAA is the professional society for aerospace engineers. It publishes the journals in the field, it puts on many of the conferences. And one of the conferences that it hosts every 18 months is a Hypersonics conference. And that conference tends to alternate between a US host and then an international host. It's been held in places like Australia, Scotland, and in 2017, China asked to host the conference. Now, what I have plotted here are the publications from the United States in blue, China in red, and then the number 3 country is Germany, and that's in this greenish color. And you note that the number of publications coming out of China have risen dramatically. This is unclassified, by the way. This is mostly universities. These are university students and their faculty members publishing. So you can see the interest that was generated from around the world. And by the way, there's part of me that says, hey, good on them. They've seen the potential of this area. And that, as you can imagine, that got a lot of attention. So in 2016, I was on a panel from the National Academies where we did this report where basically we were funded by the United States Air Force. And they asked the question first, actually several questions. First, should we really be worried about this? Should we be worried that other nations are investing? And then second, if we are worried, what are the implications? You know, what exactly do we need to worry about? And then the third thing is, what do we do about it? So we wrote this report, and we had several conclusions. The first was, yeah, this is something you really need to worry about. Because a hypersonic system is more than just high speed. It combines speed, but because it's in the atmosphere, it can also be maneuverable. And it can also operate at particular altitudes that make them hard to detect, but also hard to stop. So that was one message that we gave to the Air Force. The second thing we told the Air Force was, yeah, those nations like Russia and China and other countries, they've invested heavily. They have realized the importance of this, and in many cases building on U.S. efforts, and their investment profiles were much higher than we were investing. And the final point we made was, this is a serious threat. This is something that we really need to be paying attention to. And we also told the Air Force that this is more than an Air Force problem. This was a whole of Department of Defense problem. I've shown you, by the way, when you go to the website of the National Academies, when you look at there's a web page where you can download reports, and they very kindly tell you the number of reports that get downloaded. And so, you know, when you work on a report, you can kind of see, did anyone read it? Did anyone care? This report, and this number is already outdated, they're already up to almost 6,000. This report was downloaded 6,000 times. A typical National Academies report will maybe be downloaded about 100 times. So this thing got a lot of attention. The other fun thing that the Academy does is they'll actually plot out, based on IP address, countries where the report is being downloaded. And so, yeah, the United States, that's big. Russia's big. China's big. Australia's big. India's big. So I think it got a fair amount of attention worldwide. So I want to come back to now, what do we do about this? How do we address this issue? In 2004, we showed beyond any doubt that this technology works. That was the X-43. I sometimes refer to that as the Kitty Hawk moment. It was like the Wright brothers standing out in North Carolina. They flew their airplane, they showed that it worked. In 2010, we flew the X-51, and that showed that not only do scramjets work, but they can work for long duration. I sometimes refer to that as the Charles Lindbergh moment. What did Charles Lindbergh accomplish? He wasn't the first to fly by any means, but he showed you could fly an airplane for long duration and cross the Atlantic Ocean. And once he did that, he opened up air travel around the world. I mean, you look, as soon as Charles Lindbergh crosses the Atlantic, there's just a whole number of people who also start flying across the Atlantic. It opens up this whole idea of air travel over long distances as being practical, and that's what X-51. And then most recently, in 2021, the Raytheon Northrop air-breathing Hawk vehicle flew. And what did this accomplish? Well, this was actually an advanced design that built significantly on that earlier X-51 geometry with many improvements. It flew 17 years after X-43, but incorporated a lot of lessons learned and showed how mature our design methodologies are. The duration of flight for this vehicle is still classified, but I can tell you it went much further than X-51. So kind of that, in the same spirit that once Lindbergh started flying, other people started accomplishing it. Well, once we flew X-51, other people acknowledged you can fly for long distances. The result is that we have a lot of programs in the United States today that are addressing hypersonics. Last year, the General Accounting Office was charged with doing a report on the state of hypersonics, and particularly looking at government programs. They identified 70 separate Department of Defense programs that covered hypersonics. Some of them are small, some of them were university programs, some of them were pretty large, but it shows you that we've got a pretty rich investment right now underway across the field. There are a few that I'm particularly proud of. One in particular is this program right here, the University Consortium for Advanced Hypersonics. That was the idea that we need to get universities engaged in this field in a way that they have not been engaged in. And So the Department of Defense basically set aside about $100 million to fund a consortium of universities that would work on problems of direct relevance. The consortium was awarded to a team that was led by Texas A&M, but the Ohio State University is an important participant in this consortium. They're now up to, I think, the last number I saw was 93 separate universities involved in this, and now industry partners are coming on board. And this is also going to address our workforce issues to reinvigorate students working in the field. The situation is so good that the services are actually fighting over who loves hypersonics more. That's how you know your research area is successful, that they're actually fighting over it. The Army has a program called the Long Range Hypersonic Weapon, where they want to shoot hypersonic missiles off of trucks. And earlier this year, the Air Force actually got kind of pissed off about that. And you had the unusual public airing of concerns where you had Air Force officials saying, you know, that's not really the Army mission. The Air Force does the long reach, the Army is on the ground. And I have to say, you know, stepping aside, even though of all the services, I'm going to admit I love the Air Force most, but I got to admit, it was fun to watch this play out. My analogy is it's kind of like, you know, the guy who has two girlfriends fighting over him and the girl who has two boyfriends fighting over them, or whatever mix and match. You know, it's like, wow, you know, everyone loves us. They love us so much they're fighting over who loves us more. So that's actually a pretty good situation to be in. Something else that's interesting that has happened. In addition to investments from the government, we are seeing private industry stepping up and putting real dollars into hypersonics. On your left is a picture of an airplane that is being built by a company called Stratolaunch. So, quick little history of Stratolaunch. Stratolaunch began as a pet project of a billionaire by the name of Paul Allen. I'm sure many of you have heard of him. Paul Allen was interested in spaceflight, and so he decided to spend a part of his fortune building an airplane that is basically the world's largest airplane by wingspan. It's actually the size of two 747s joined by a center wing. And Paul Allen wanted to use that to launch rockets into orbit. So the idea is you would sling a rocket in the center wing section, you get it up to altitude, then you drop the rocket, light it off, and it carries a payload into orbit. Paul Allen died. His heirs weren't at all interested in the company. They were going to shut it down. Instead, they sold it. It got picked up by a venture capital firm called Cerberus Capital. And the head of Cerberus Capital said, hey, we're going to rebuild this, we're going to reinvent this company to do hypersonic flight testing. So today, this airplane, which is built sitting in a hangar out in the Mojave Desert, is being redesigned to do hypersonic flight tests, to carry hypersonic vehicles. And they're actually building the hypersonic vehicle. They've got a small-scale vehicle that they call the Talon, T-A-L-O-N. It's going to be a wind tunnel in the sky. It's going to be a flying test bed that's under construction as we speak, purely on private equity. Really interesting. Similarly, there are universities that are stepping up. So, am I allowed to mention Purdue University in the state of Ohio? So, Purdue University just announced that they're working with Rolls-Royce and Indiana State Government to build a new test facility called the Hypersonic Ground Test Complex that will allow the testing of new classes of hypersonic engines. Really exciting endeavor, and the biggest investment for that is coming from the Rolls-Royce Corporation. So again, you're seeing private industry stepping up. Now, why are they doing this? Well, neither of these companies are charitable organizations. They're doing this because they see the potential for eventually government investments. This is an initial outlay that they're making in the hopes that they're gonna have government customers. All right. So let's pose some remaining questions, and we'll see where we are, and then I'll open the floor for questions. Where are we right now in terms of support for hypersonics? Well, you know, as I mentioned, if we look at the funding cycle, it tends to be periodic. So is the support going to continue? Right now, the Department of Defense has allocated almost $25 billion for hypersonics over the next 5-year period. It's more than we've ever had. The Department of Defense thinks in 5-year funding chunks. All right, will that continue? Well, in early 2022, the new administration announced its funding profile for hypersonics, and they didn't decrease funding. In fact, they kept it exactly where it was from the previous administration, so that's a really good sign. Heidi Shue, as I mentioned, the current Undersecretary of Defense for Research and Engineering, came out with very strong statements recently about hypersonics. The Deputy Secretary of Defense, Kat Hicks, who's the #2 person in the Pentagon, also has spoken in great support for the field. The last guy that I've got to mention there, Frank Kendall, is the current Secretary of the Air Force. Him, not so much. He's been saying things that have some of us wondering, scratching our head. He's been sort of positive, but not. So we're a little bit cautious on that one. But overall, there's reason to believe that political leadership is fully engaged and fully supportive. To the point where I think it's fair to say this time is different. We're not going to see a downturn in funding. Now, of course, you always have the skeptics, and hypersonics is not without its skeptics. About a year ago, 2 authors published a paper under the auspices of the Union of Concerned Scientists, where they questioned the whole field. And it was kind of frustrating because it was a really, really bad paper. I'm not just saying that because I'm a hypersonics guy. It never would have made it through peer review in the Aerospace Journal. But it received a lot of attention. It was on the front page of the New York Times. So you still find yourself battling some of these issues. Other questions that come up. So if we're going to do hypersonic systems, can the defense industrial base actually scale up to supply the needs of the government? Think about a hypersonic boost glide system. It's flying at very high speeds. It's getting really hot. It needs to be built out of high temperature materials. Building one demonstration vehicle is very different than producing 100 or 1,000 missiles. That's a whole different level of manufacturing. And a lot of questions are being raised whether the U.S. defense industry right now can step up to the plate to provide those capabilities. At NDIA, we're actually doing a study exactly along those lines to assess the state of the industrial base to meet those needs. Test infrastructure. It's both ground test and flight test. Wind tunnels. We spent the last 2 decades shutting wind tunnels down around the world, around the country. We were shutting down wind tunnels at about the same rate that other countries were building wind tunnels. So now we find ourselves in a situation where we don't have enough wind tunnels to do the testing that we need to do. Right? Our programs are actually climbing over each other, desperately trying to get test time in our wind tunnels. So that's why we're seeing a reinvigoration, a refocus of attention on rebuilding wind tunnel infrastructure. And then certainly flight test. In the days of the X-15 that I mentioned, we were flying at a rate of about once every 2 weeks. Now we're flying once every 6 months. If we're going to make progress in this field, we need to be flying on a much more regular basis, which means we need to have repeated access into the hypersonic flight partner. We would like something that, such as the Stratolaunch vehicle, is so important, because that's a vehicle that will allow us to fly hypersonic vehicles on a much more regular basis. International engagements, really important. We're not in this alone. We've got really strong partnerships in hypersonics. The Australians, remember I mentioned the Australians for the first scramjet? They're still very closely engaged with the U.S. research community, to the point where the Australians are actually members of that university consortium that I mentioned. Some discussions about escalation versus de-escalation. Is this a technology that's getting out of hand? That's a subject for a whole different lecture, but there are some policy implications. If we continue to develop hypersonic technologies, does that trigger a new arms race? Are we already in an arms race? And we're playing catch-up. And that has led to some folks asking about whether maybe we can solve hypersonics by simply agreeing not to build them. We sit down with our peer competitors and we get everyone to agree that this is not a technology we'll continue to pursue. I'm just an engineer, I'm not an ambassador, I'm not a diplomat, but I think that one's pretty unlikely, especially when we frankly are at a disadvantage in this. All right, so I get off the stage slide. Where do we go from here? There's a number of things. One is, we've done the demonstrations. We've done the individual flight tests, the X-43s and the X-51s. Now we can do this at scale. By scale, I mean fly lots of numbers, fly early, fly often, and not only expand out the envelope, but learn how to produce these things in numbers that are meaningful. We need to go to reusable systems. But so far, everything we've flown gets thrown away after you fly it. The X-43 flew at hypersonic speeds, crashed into the ocean. X-51 flew at hypersonic speeds, and at the end of its flight, crashed into the ocean. The most recent DARPA Hawk then, same thing. We flew it, we crashed into the ocean. Having a reusable system is really important from many standpoints, not just reducing the cost of operation, but also you learn a lot more when you can get it back and look at it. So that's an obvious direction that we need to move in. New propulsion systems. I talked about only one type of hypersonic propulsion system, the supersonic combustion engine. We know we can build it, we know we can fly it. But those engines only work at hypersonic speeds. It's fine for a missile that's flying only at Mach 5. It's not fine for an airplane that's got to take off from the ground. It has to begin operating at Mach 0, accelerate up to hypersonic speeds, maybe do a mission, maybe deliver a payload, and then land again. So you need some engine system that can cover the entire Mach number range, which is almost certainly going to use some combination of engine systems. Probably a turbine-based system, a turbojet, that then transitions to a ramjet or a scramjet. And then finally, we can't give up on researching alternate propulsion flow paths. Right? We think the scramjet is the engine of choice today. It's a very simple engine, it's been proven, but maybe it's not the best one. Maybe it's not the best configuration. And so always looking for these alternate propulsion flow paths. Kind of important. Here I got a picture from a company that's based in England called Reaction Engines. They have an entirely different approach to flying at hypersonic speeds. They have essentially designed a very, very efficient cooler. That cooler sits at the front of an engine. Air comes into the front of the engine, and that cooler liquefies the air. They gather the liquid oxygen, and then they can burn it with a very conventional engine. Another way to think about the way that engine works is because they cool the air that comes in the engine, they trick the engine into thinking it's flying at a lower speed. It's a pretty good trick. That's not a new idea, but what is new is the folks at this company have figured out how to build this heat exchanger, this cooling system, to make it very compact, very lightweight, and very efficient. And a couple of years ago, they opened up a U.S. subsidiary in Colorado that has built a test cell, and they're exploring all sorts of concepts. So maybe there's a whole different approach to flying hypersonic speeds. And then finally, I want to bring you back to an early picture, an early description, which is, will we ever get ourselves to the point where we're building hypersonic vehicles that can indeed fly all the way up to orbit? Think about what that would mean. If you could fly to orbit in a vehicle that more closely resembles an airplane than it does a rocket. Today, when we launch something to orbit, we put it on a rocket that requires thousands of people to prepare for flight. It can take months to get a rocket ready for flight. Compare that to an airplane. Right? You go to the airport here in Columbus. Airplane lands, taxis up to the terminal. Passengers get off, bags get off. They clean the toilets, hopefully. Passengers get back on. 15 minutes later, that airplane's ready to take off. It's airplane-like operations. It's a very different model from rocket operations. So if you could operate like that, think about what that means for access to space. Think about how routine spaceflight could become. It's a very, very distant vision, but it's not beyond the realm of the